In 1897, J.J. Thomas discovered the electron. The atom was divisible after all. And at the birth of the new century, Planck's own mathematical constant was arrived at when solving for the issues surrounding the ultraviolet catastrophe, thus suggesting the quantization of energy. But even at the time, most physicists, including Planck himself, assumed that this thinking was purely a mathematical derivative, non-reflective of true nature, though it would only be a few short years before the insights of a 26-year-old patent office clerk would finally make sense of these uncomfortable resolutions, not only by redefining the universal stage of the 2,000-year-old ether, but by totally reshaping our understanding of light, matter, energy, and even space and time itself. 1905 was a year that would come to be known as Albert Einstein's Annus Mirabilis, his miracle year. By June, he had re-established our fundamentals of light. By July, our understanding of motion. By September, he had rewritten the rulebook on space and time, and by November, he had toppled matter and energy itself with his famous equation, E equals mc squared. Within mere months, this then entirely unknown enthusiast had entirely changed the way we look at the world. The first of his seminal, though slightly dry in title, papers was on a heuristic viewpoint concerning the production and transformation of light. A paper that not only landed him the Nobel Peace Prize, but redirected our discussion on light yet again by solving a perplexing quandary known as the photoelectric effect. The predicament came about when experiments in the 19th century showed how electrons could be knocked away from various metals when hit by electromagnetic radiation, or in simple terms, when the metal was lit up by light. The curiosity compounded, however, when the kinetic energy of these escaping electrons appeared totally unaffected by the light's intensity. The amplitude or brightness of the light did show to affect the amount of electrons being released, however it did not affect the electron's capacity for being released in the first place. The only aspect of the light that appeared to have this effect was the light's frequency, in other words, its colour. If a particular colour of light, say blue, could knock the electrons away, then even the faintest beam of light would be effective. But if the colour, say red, did not influence the electrons, then it would make no difference at all how intense the light was, how bright, how much radiation and energy were emitted, the electrons would remain bound to the metals. Einstein's paper solved this issue, but not before a heretical throwback to Newton's particle theory of light. At a time when light was more than proved to be wave-like, Einstein, inspired by Planck's suggested quantizing of energy, theorized that when thinking of light as packets of energy, which he called quanta, we could more easily solve the riddle of the photoelectric effect. Because if the radiation were to be considered particle-like, then each packet of quanta would have its own unique value of kinetic energy, an energy intensity that was defined by its frequency, its colour. And so, if this individual quanta held within it the energy needed to dislodge the electrons from the metal, it would. And the brighter the light, the higher the count of quanta. Hence, the higher amount of collisions it would lead to the shedding of electrons. But in contrast, if the individual light quanta did not host enough kinetic energy, again as a result of its frequency or colour, then it wouldn't matter how many quanta got sent hurtling into the metal, none would individually have the energy needed to dislodge an electron. The upshot of which meant that light, here we go again, was not in fact a wave. But this time, it was not quite a particle either. It seemed that for the first time, it was both. In specific experiments, these quanta, which came to be known as photons, would reveal attributes associated with particles, and in other experiments they would appear wave-like. It turned out that there was simply no rule in the book of the universe that stated that light must be either one or the other. This was something new, something unique to our understanding and experience, something we still fail to fully understand today, as can be appreciated in the clumsy language used to describe the phenomenon. A language resolved to the new norm but stubborn to let go of old perspectives. It's what we now refer to as wave-particle duality. Light is not a wave, but nor is it a particle. Some might say it's both, others say it's neither, because it's a blending of the two ideas, and yet also something wholly unique. A realization that would come to influence our entire picture of reality. But Einstein was not yet done. By September of that same year, Einstein had published his third, yet still dryly titled paper, Zur Elektrodynamik bewegter Körper, on the electrodynamics of moving bodies. A paper that was to again ask the question, to what background medium must the speed of light be measured? The answer to this riddle was arrived at when Einstein assumed that not only was light restricted to this singular speed, but so too were all things. The universe had a speed limit. The more discombobulating interplay that arose as a result of this universal speed limit was that, as discussed in Chapter 3, when any matter is either increasing or decreasing its velocity, its flow within both time and space will equally be affected. So that as we ever encroach upon the uppermost extremes of this universal speed limit, physical space will literally contract, whilst the relative flow of our time slows, countering any hopeful seizing of the limit. In accordance with Einstein's rules of relativity, no thing that hosts mass can ever successfully increase to or above the speed of 299,792.458 kilometers per second. Because if it did, not only would it require an infinite amount of energy, but at the speed of light, any distance between objects would collapse to zero, and time would essentially stop moving relative to that frame of reference. In this sense, space and time themselves do not exist beyond this speed. And in the century that followed, experiment after experiment has repeatedly confirmed that this is precisely what happens. But this is still a confusing idea, because after all, are we not moving, as is the planet, the galaxy, and all contained within? But if we are moving, then why do we not experience this slowing of time ourselves? Well, this is precisely the point, as the effects of time dilation are not experienced from the point of view of the accelerating observer. From our perspective, time will flow as it always has, at the speed of time. But if this time dilation is not experienced from the perspective of the first person, what exactly is this time dilation in relation to? As with the question, to what background is the speed of light measured, we can equally ask, to what background is the passing of time relative? The answer is that it is relative, and hence relevant only to the other objects existing within spacetime. Surprising though it may be, according to Einstein's theory of relativity, there is no space-time. The so-called space-time that physicists like Einstein so often refer to is not a physical thing like the luminiferous ether. It is simply the mathematical manifold or construct that we use to appreciate the relative differences between two unique perspectives moving in respect of one another, not in respect of space-time or any other background ether. Each particle's position within space-time is relative only to the other particles. But this is not suggesting that between these particles is merely empty space, as it is not a universe of energy floating upon space-time, but rather it is a dense bed full of energy, matter, velocity, space and time all whipped up into a single unified flux of happenings. Nothing is separate from the whole. Not matter, not even light. The energy that has given rise to the photon of light is the same energy that exists between each quanta of energy, and the same which gives rise to our physical reality on the whole. Each vantage point, each perspective from within this manifold of space-time relates its appreciation of space and time to all that is within and without it. In the century most recently past, we've come to understand this flux of the universe better than ever before. The insights of French physicist Louis de Broglie, first presented in 1923, showed us that not only does light possess an underlying property of wave-particle duality, but so too do all particles and hence all matter. And with this new idea, the world was set for the quantum revolution. If you enjoyed that and you would like to watch the next part, I'm going to put the links below. Otherwise, the full 1 hour deep dive into the history of light is currently available on our homepage, so feel free to check that out. Otherwise, much love, and I hope you all have a wonderful, wonderful week. See you later.